Welcome everyone to this week's Autonomy Talks. This week is a great pleasure to have with us Professor Sanjiban Choudhury, who is an assistant professor in the Department of Computer Science at Cornell University, and also is a research scientist at Aurora Innovation. So something about Sanjiban, he did his PhD in robotics from Carnegie Mellon University, and then was for a while a postdoctoral fellow at the University of Washington. At Cornell, he leads the Portal Group, which is a group that builds everyday robots for everyday users. And in this context, his research focuses on imitation learning, decision making, and human-robot interaction. As you have seen in the bio, his work has received a number of awards, and also he's a Siebel Scholar class of 2013. Today he's going to talk about the virtues of laziness in model-based RL. While reading the abstract, I felt intrigued and I'm excited to hear more about it. And also, Sanjiban said you're free to ask questions during the talk, so if you have any, feel free to post in the chat and I will read them for you. Without further ado, Sanjiban, go ahead. The stage is yours.
Thank you, Jayla, for the wonderful introduction. Good afternoon, everyone. Thanks for coming to the talk. I know tomorrow's NeurIPS and people must be very busy, so really appreciate the time. Yeah, today I'm very excited to talk about this paper that we've been working on for almost a year and are presenting this year at ICML. It's on the virtues of laziness in model-based reinforcement learning. And I'm super excited about this paper. I think this has the potential to be one of the, a fundamental contribution to the field of model-based RL. Of course, this is joint work with an amazing group of people, notably Anirudh Vemula, Yuda Song, Arti Singh, and Drew Bagnall. Okay, so before we dive into the details, the heart of this talk is going to ask a very fundamental question this goes beyond model-based RL, which is actually related to planning. So the question is, can imitation learning help us break the exponential complexity of planning when we apply it for model-based RL? And we'll answer this question as a big yes, and in fact show that it's not just relevant to model-based RL, but it's actually relevant to the field of imitation learning, which also has a very close problem that we'll discuss today. Okay, good. Okay, but before that, who are we? I'm Sanjiban. I lead the Portal Group here at Cornell, the new lab. We are, a small group of people who are building a lab that's building a set of robots that's designed to help everyday users do everyday tasks. Okay, so our mission is to equip robots with skills to work with and around people. Imagine your grandma at home. We want to help her live a better quality of life. And so our goal is to build robot apprentice that can do the kind of tasks that she wants done around the house. So, she has a bunch of tasks in her mind. These tasks involve working with and around people. And the goal of our lab is to build a robotic stack that can interact with the human to understand these tasks and execute it. Sort of the overall goal. And the way we philosophically approach this goal is we look at it through the lens of three concrete thrusts. So obviously, the first task is we want a robot that can do a wide variety of high-level tasks that the human wants done in the home. For example, setting the table, cleaning dishes, cooking recipes, and so on. And a big part of that is interacting with the human to understand the tasks they want. So high-level tasks is a big part of what we do. Of course, we are building a physical robot that has to actually do these tasks in the real world. So a second component of this work is endowing the robot with a library of low-level skills. For example, you're seeing policies for cleaning the table, dragging the cart, picking up cups, and so on. Skills that it can kind of compose together to do any high-level task. And finally, the robot is not working in isolation. It actually has to work alongside humans in home environments. And so modeling humans is a big part of what we do. So these are sort of the three principal thrusts that we are focusing on in our new lab. But today's talk is going to be very fundamental. It's going to talk about models that I'll argue in a bit is at the heart of everything we do in the lab. Okay, so what do I mean by this word model? It can be very overloaded. So I concretely mean model in the context of a Markov decision process. So, we can formalize many of robot decision making as an MDP, where you have states, actions, transition functions, and a reward. And it's the transition function that I'm referring to when I'm using the word model. So here we have, our robotic manipulator, Dora, that's manipulating objects like picking up the ladle. So we can think of, sort of formalizing this sort of policy as having a state, the robot having a state. So here state can be the joint configuration of the robot, as well as the state of any objects in the world. And actions can be the torque that the robot applies. For example, pinching the object and lifting it up. And a model simply says, okay, given state and actions, what are likely next states? So in this case, the applying a force upwards results in the object moving up and so on. Now, there are many interesting questions that one can ask about what makes a good state. That can be a topic for a whole other talk. But for the context of this talk, we're just going to focus more on models and talk about, given some state representation, how do we learn this prediction of what the next state is going to be? Okay. So, like I said, models are at the heart of everything we work on in the lab. And what do I mean by that? So, when we think of models, the most natural thing we tend to first think about is models of the physics of interactions. So when we think about low-level skills, we think about building models that can tell us how actions change the state of objects in the world. So that's one definition of models. But models are more broader than just physics. For example, when we think about high-level tasks, we can think about models of how high-level propositions evolves with action. So this is somewhat more abstract models. And finally, when we think about working alongside humans, models tell us how humans might respond to motions that the robot can make. So we typically refer to this as forecasting, and models play a big role here. So hopefully I've convinced you models are important in more than one aspects in robotics. So yeah, why do we work with models? So I guess I'm talking to a group of roboticists, so I don't have to sell this too much. But I mean, the crux of it is robots can't just try out random actions in the world. They need to reason about the consequences of what they do. So models are very necessary. For instance, without models, you would have home robots blowing up kitchens, or you would have self-driving cars causing mass accidents on the roads. Models are necessary for robots to detect consequences of bad actions and not take them. So models are necessary. Almost in every real robotics product that I've worked on in the past, we have invested heavily in simulators to verify behaviors before deployment. So I spent my PhD working on these kind of full-scale helicopters, and a lot of the time was spent in building simulators where we could simulate the consequences of robot taking various actions. I've spent the last, as Julie mentioned, I've been working for the last few years at Aurora, where we work on self-driving, and almost every self-driving company invests a ton of resources in developing simulations of other actors, of the robot, and so on. So, so models are necessary in practice as well. Models are great from a theory standpoint. So from time and time again, theoretical RL papers have shown that model-based reinforcement learning is minimax optimal, and in some sense is sample efficient, and it is in fact the right thing to use as opposed to kind of using model-free methods. So models have a solid foundation when it comes to theory. And recently, models have been working really well in practice. So for those of you who are up to date with the latest developments in the dreamer world. We've seen these remarkable results where model-based RL has been used to solve very difficult exploration problems. For example, mining for diamonds in Minecraft. And they're exciting results. So it's an exciting time to work in model-based reinforcement learning and sort of combine good theory with good practical algorithms that can hopefully solve complex long horizon tasks that model-free methods typically struggle to solve. Okay, good. So hopefully we're convinced models are important. How do we go about this process of learning models? Okay, so I think a good place to start would be to go back in time and talk about some of the foundational work in model-based RL that came out of Stanford from the work of Peter Beal and Andrew Ng, where they were training controllers for a helicopter to do acrobatic maneuvers. So the way they went about doing this is, they got a expert pilot to come in and control these sort of RC helicopters and do all sorts of interesting maneuvers. And then they showed that they were able to take that data, train fairly simple models of helicopter motions, and then fairly simple controllers to be able to do some of these acrobatic maneuvers, like these sort of stall turns and tick-tock motions and inverted takeoffs and so on. Really like watching this video because I have a soft spot for helicopters. But yeah, this was some work very early in the day that showed the power and the promise of model-based RL. Okay, so let's dive a little bit deep into the general strategy that's applied. Doing model-based RL involves two fundamental steps. The first step is you have to go learn a model. So the way they went about doing this is they wrote down the equations of helicopter flight and did a very simple least squares fit to solve for the unknown parameters. So they've learned a model. And then they applied ILQR to plan with this learned model. ILQR is a fairly standard MPC technique that you can use once you have a learned model. And then the combination of these two was good enough to solve the task we just saw. Okay, so this suggests a strategy that can be almost the first strategy that many practitioners come up with, which is train a model on, go use an expert to collect a bunch of trajectories and train a model on the data that you collect with the expert, right? So I'm going to call this this strategy model-based RL version 1.0. Okay, so the pipeline is ask an expert to collect data, fit a model using supervised learning techniques on the data you collected, and then finally plan with the model. Now, for those of you who are looking at this diagram, you might be thinking, hang on a minute. We've seen time and time again a fundamental issue that makes decision-making, machine learning and decision-making different from machine learning in supervised learning setting is this issue of train-test mismatch. How do I know that if I apply this process, the test distribution that my learner sees will not vary from my training distribution? And my response to that is, I understand, I hear you. So I'm going to add a condition and say, I'll do such a good job of training a model that I'm going to drive training error and validation error to zero. Okay, not epsilon, completely to zero. So if I perfectly fit a model, then this strategy in principle should work, right? I collected data from an expert that's flying optimally. I perfectly fit a model on that data, and now I'm planning with that model. And if the error is zero, this should work, right? Well, the answer is going to be no. And this is the beginning of what starts to make model-based RL very interesting. So to show you the problem, I'm gonna show you a toy MDP. So we have a very cute robot on the left trying to get to a trophy on the right. This is a very simple chain MDP. So the expert always takes one action, which is going to the right. Okay, so the expert keeps taking the action, go right, go right, go right, all the way to the goal. All right, so you collect this data from the expert, and you train a model that M hat that perfectly agrees with the transitions it observes from the expert data, right? So you train, so your model M hat perfectly agrees that if you take the right action A, you go to the next state, okay? And training error is 0, validation error is 0, and so on, okay? But what if the model learns a shortcut inadvertently? So in its attempt to drive training error down to 0, it learns that there exists an action A prime that can shortcut me from the second state all the way to the goal. In other words, your model becomes optimistic, okay? Now notice that because you don't excite this action at in your training data, you don't actually see the consequences of this incorrect prediction, right? As far as you're concerned, the expert never took action A prime, and so the error is, so the validation error for your model M hat is still 0, okay? Now, if you plan with this action, obviously, in reality, taking action A prime, taking this shortcut ends in death, and so your model performs terribly, okay? All right, so, in other words, being optimistic is fatal for your model, and Ross and Bagnall actually showed this. So, you know, this is some very retro video of helicopter flight, so the graphics might be interesting. But this is a video of training data where an expert. So this is a simulation video, obviously. This is training data of an expert flying a helicopter in a funnel. And they applied the strategy we just saw, so model-based version 1.0. And the controllers seemed to be doing fine initially until it took an action that took it off this funnel, and then it crashes. Okay. So this is this problem of the model learning these kind of shortcuts is a very real problem that's been observed time and time again. Okay. So that strategy was a bust. The natural reaction to the strategy is, of course, we have to train a model not just on the state actions that the expert visits, but on the state actions visited by the learner, right? So the key idea is the problem is that the expert data was perfect. It perfectly followed the funnel. But at test time, when the model tried an action A prime, it hadn't seen a train time. It deviated from this funnel, and it simply didn't have data in this regime. As a result, it made mistakes, right? So the natural strategy to mitigate this is we must collect data on policy, on states the learner visits. So this gives rise to model-based RL version 2.0. Okay, and it's a very simple framework. You begin with some policy, go collect data, fit a model on that policy, plan with that model, collect data, and keep repeating. Now, for those of you who are familiar with imitation learning literature, there's a parallel algorithm called Dagger that's very much similar in spirit, except here we are fitting models instead of policies as you do in imitation learning. Okay. Okay, so again, I can ask this question that if I were to apply model-based RL version 2.0 and perfectly fit a model, so drive down training and validation error to 0, this idea should work, right? I mean, unlike last time, now I'm actually training my model on the state action distribution it visits. Okay, so there's no more train and test mismatch. If my test error is 0, I should have the right model, correct? Wrong. So let me again convince you why this idea doesn't work. And in some sense, this is why model-based RL is interestingly different from the imitation learning theory that we see. So again, let's go back to our example. We have the robot on the left and a trophy on the right. Now, let's say the robot learns the following policy, or learns the following model rather. It learns a model where if it keeps taking action A, okay, it goes right the first 2 times, but eventually it action A ends up in death. And notice that that's actually an incorrect model, right? We know in reality, taking action A gets you all the way to the trophy. So the model is incorrect in learning this transition to death. However, the model has learned a transition where taking action A prime from the root node gets it to this $1 bill. Okay. I want you to ask, I want you to think, if I were to plan with such a model, what would the optimal policy look like? Well, the optimal policy would look like take action A prime instead of taking action A. So the optimal policy will basically say, don't take action A, take action A prime, go for the $1 bill. In reality, if the model were to take action A prime, it realizes, it sees that the real world transitions agree with the model, right? So taking action A prime does indeed get it to a $1 bill. So test and training error is exactly, or test and training distributions have matched. The model fit error is 0. But the model has clearly learned a non-optimal policy, right? And the fundamental reason here is the model is pessimistic. So the model incorrectly learned that taking an action A would result in death. So it settled for less. It settled for going for the $1 bill, which happened to agree with reality. If only it had tried action A, it would have realized that this pessimistic model is wrong, right? So fitting a model only on states the policy visits can result in can also result in not learning the optimal model. It's really interesting. This is so I guess the lesson from both of these problems is that you shouldn't be too optimistic. You shouldn't be too pessimistic either when you're thinking about fitting models. And you know, this is life lesson from math, as it were. Okay.
Dr. Choudhury, quick question.
Yes.
So my name's Manu, and
yes.
So we assume that the model is sufficiently descriptive of the system here, right?
Yes.
So, for example, if the helicopter did not know about gravity, or so then it would not know that when it's coming down, it would not be able to learn or match that parameter, right? Okay.
Right. So here in this particular case, I'm assuming for this example, we're in the realizable setting. So the model has enough capacity to explain the real world data. And purely what we are observing is the importance of the distribution on which you're fitting the model. So we tried 2 strategies: fit a model on the distribution that the optimal policy visits, and we saw that results in optimistic models that are incorrect. We then said, okay, fit a model on the distribution that the learner only visits. We saw that we learned pessimistic model that's incorrect. And so the distribution is going to be very key here. Does that answer the question?
Yeah, thank you.
Perfect. Awesome. Okay, great question. Yeah. Okay, so we've tried 2 strategies, both were bust. The strategy we are left with, and the thing that works, is training a model on state actions visited by both the expert and the learner. And so, you know, broadly, this strategy is called model learning with planner in the loop, where the idea is you begin by collecting some expert data, you fit a model, you plan with the model, execute the model in the real world, and then you fit a model on both the expert data and the data you collected from the real world, right? Both of these data sets should be given equal importance when you're fitting a model, okay? And if you do this, and if you drive down error on both these data distributions, you can prove that you will indeed, in the realizable setting, recover the true model. In the agnostic setting, you will have some agnostic guarantees. Okay, and just to sort of close the loop, this is what happens when you train a model in this manner. So you're, again, we are seeing this nose and funnel, but here we are seeing a model that's been trained both on expert data and on data the policy visits. And even though this sort of helicopter deviates from this kind of funnel-like maneuver, because it's trained on both data sets, it's sort of trained to both minimize error on states it visits while not being overtly pessimistic. Okay. And this is not just sort of a heuristic. There's actually very solid theory behind this that justifies this approach, which we'll touch on in a bit. But I encourage you to learn more about the theory. I encourage you to read this paper called Agnostic System Identification for Model-Based RL. In some sense, it's if for those familiar with Dagger, this is sort of the sibling paper of Dagger that's a little bit more interesting because of the complications that arise when you're fitting models rather than policies. So this sort of justifies why you need to minimize errors on both of these data distributions. And so for 10 years, this was in some sense the foundational theory on which model-based RL kind of rested on. I mean, there's been a lot of work on representations for models, on playing with different losses, but when it comes down to analyzing performance guarantees of model, this was sort of the theory paper we went to. And oops, sorry. I think okay, I'm gonna there's some problem in the slide, but that's okay. I'm going to give you a hint for what the for what the theory says about fitting models. And so I'm going to introduce a lemma called performance difference via planning in model. So there's going to be a bit of math, but not to worry. I'll try to explain the intuition behind the math. Okay. So the way we judge the goodness of a model is by looking at a term called the performance difference. So that's shown in the slide at the top. This basically says, what is the performance of the optimal policy pi star in the real world M star minus the performance of the policy that we compute in the real world, okay? And all roads lead to this performance. This is the ultimate thing that we care about, bounding this performance difference between the optimal policy and the policy we compute, okay? Now, Ross and Bagnell showed you can break this term down into 3 components. The first component is your planning error. That says, how good a job are you doing in terms of finding the optimal policy in your model, okay? So that's the first term. The second term is talking about how good a job are you doing by fitting a model on states that your expert visits, right? And the third term is how good a job are you doing on fitting a model on states that your learner visits. So and the sum of these 3 terms bounds the performance difference. So hopefully by looking at this equation, you can get a sense of why the math says we have to train our model both on data that the expert visits and on data that our policy pi hat visits. Okay. Okay. So in our example before, we were able to drive the second and third term down to a very small value, and we're able to plan optimally inside our model. So if all 3 terms are low, you can prove that you match the performance of the expert in the real world. Okay. Now, all right, so this is all good, but this is theory that we have known for 10 years. So what is the challenge? Why is this, what has fundamentally been the challenge in model-based reinforcement learning? And the challenge, which is familiar for those of us who've worked in planning, is that planning is hard. Planning is trying to find a needle in an exponentially large haystack. The needle here being the optimal path or the optimal policy, the haystack being the space of all paths or all policies. So planning is hard, there's no way around it. And so, if you go back to the equation, if you go back to the equation here, asking our learner to make planning error small is like asking it to solve this really hard problem of finding the optimal policy, right? That can be computationally very expensive. Okay, so to motivate why it's hard, we're just going to look at a tree-like MDP. So here's a tree MDP. It's a very simplified MDP where you have 2 actions at every state. You can either go left or right. Okay. So the branching factor of the tree is 2, and it's of depth t, t being the time horizon. Okay. So I've constructed this tree MDP in the following way. So let me just walk through it. On the leftmost leaf node is the pot of gold. Okay. The robot starts at the root node. And on every other leaf node, you end in death. Okay. Except there is a $1 bill in the in some of the penultimate leaf nodes to, which will play a bit of a role in a second. Okay. So this is the tree-like MDP that we're going to examine to understand the pains of or to understand the ramifications of this exponential complexity of planning. Okay, good. So planning is exponentially hard. So every time you call your planner to find the optimal policy, it has to visit every single node in this tree to eventually figure out that the optimal path is to go on the leftmost branch and reach the pot of gold. Okay, so so planning is hard. And the question, I guess, is how much planning do we need when we are learning, when we are doing model-based RL? Okay, so right. So let's just to recap. Planning is, we are examining this tree-like MDP. We know that planning is complex in this tree-like MDP. We know that we are going to be calling, when we are doing model-based learning, we're going to be calling this planning over and over again. And I think the question we're trying to ask is, do we really, how often do we need to call a planner when we are fitting a model? Okay. And I think a good intuition to have when thinking about this problem is that in practice, when you're learning models, what you observe is that models tend to have a lot of shortcuts. You can think of these shortcuts as wormholes, or I like to call them portals, where the model erroneously think it can shortcut from one state space to another because it doesn't really understand the manifold on which the real world agent is on. Okay, so this is some very beautiful artwork from a book by Kip Thorne, which I really like, by the way. But that really shows this kind of imagery of the kind of models that we learn. These sort of wormholes that they inadvertently end up learning. Okay, and so the question we should be thinking about is, what are the ramifications of this artifact where models learn shortcuts? Okay, so we're going to examine this question in the context of this tree MDP. So this is the true dynamics of the tree MDP. But when we learn a model, the model that we learn has this tendency to learn these sort of shortcuts where it suddenly thinks, for example, it can shortcut from one of the states through a portal and come out on the other side, getting to the pot of gold, right? So in practice, for example, just like the question that was asked, the model might think it can actually overcome gravity if it took a certain action and teleport to the right state, and so that would be an example of a practical shortcut. Okay, so in reality, learned models have a lot of these portals, and the question is, what happens when we do model-based learning in the presence of such portals? Okay, so let's walk through it. Let's assume this is the model that we have learned at iteration 0. Okay, now we run our planner that takes exponential amount of time, searching every node in this tree, and unsurprisingly, the policy that we learn decides it's a really good idea to take the rightmost branch of the tree, collect the $1 bill, travel through the wormhole, and emerge on the left-hand side to get the trophy, right? So that so the optimal policy thinks, yes, this is the optimal sequence of actions to take. Okay, now if we execute this policy in the real world, we realize, there exists no such portal, and so we we would eliminate this portal from our model and end up with this new model and repeat the process again, right? So we call our planner that searches for exponential t, finds a path that again shortcuts to the portal. We execute this policy in the real world, realize there is no portal, remove it, and you get the picture, right? So we are, after many, many iterations, as many iterations as the number of portals there are in the tree, we finally find a path that stays in the leftmost branch and reaches the trophy, right? Okay, so let's recap. Planning is hard. Planning is computation expensive. And we are calling such a planner multiple times when we are doing model-based learning, right? We're repeating this for as many iterations as there are portals in our model until we find the optimal model. And you can imagine if you're doing this for a real robot with continuous states and action spaces, doing this online, this can be very time consuming. And ultimately, in practice, has been a bit of has been a problem for why we haven't really managed to scale up model-based RL, right? Okay. So what is our key insight? I mean, on the face of it, this problem seems very hard. I mean, we can't do anything about the worst case complexity of planning, right? It's probably very hard. So it seems we need a different strategy to go around this problem. And our key insight was the following, that maybe we don't actually need to call a planner when we are doing model-based RL. Our key insight was, can we get away by being very lazy and not calling an optimal planner, and instead trying to leverage the fact that we actually have data from our experts. And in some sense, instead of trying to find the optimal path, can we simply lower the bar and try to just do better than the experts on states the expert visits? Okay, so I'm going to explain what I mean by laziness in this context. But before I do, this is our paper that we are presenting this year at ICML. We are very excited to present it. So if you're at ICML, definitely come talk to us. Okay, so in the context of model-based RL, how do we turn this inner planner call loop from exponential t to polynomial t? This is a very general question of what can we leverage to turn the exponential complexity of planning to polynomial complexity of planning, right? And the key insight is a trick that's pretty old and been used time and time again throughout the history of reinforcement learning, which is to change the restart distribution. So instead of starting from the initial state, restarting from expert states to, in some sense, mitigate the amount of exploration a planner needs to do. Okay, so that's going to be the key insight that's going to give us a polynomial time algorithm. And like I mentioned, this trick is fairly old, and one of the first appearances is in this paper by Drew and others from 2003 called Policy Search by Dynamic Programming. Okay, so I'm going to give a very brief recap of this technique and show how we can leverage this technique more generally to turn this exponential complexity to polynomial. Okay, so technique is very simple. As the name suggests, dynamic programming is going to help us do this reduction in complexity. And the idea is to start from the end and go backwards. So we start from t-1 and go back in time. And at every time step t, we are going to restart from the expert states that we already have, because we already have data from the experts. So ST star is the state or the distribution of states that the expert visits at time t. And we're going to start from those states and simply solve for the best policy pi t, the best one-step policy pi t at a given time t, given that we have already solved future policies at t+1 to t, right? Because we're doing dynamic programming, we are guaranteed to already have solved the future versions of the problem. So at time step t, we're simply focused on solving for the best policy by t, okay? So that's going to be the idea. Now you can see from this algorithm, since we're only solving for the best one-step policy at any given time, we are never exploring the exponentially large tree, right? So this is going to guarantee that we do at most, t² amount of computation to compute the policy. Okay, so at every time step by t, we're going to just solve for the best one-step action plus the values given our future policies by t+1 to capital T. Okay, so let's see this more visually. So we are going to apply policy search via dynamic programming given this true MDP, right? So the blue line shows the states that we already have from the expert. So the expert has already visited the leftmost branch of the tree, so we're going to leverage that. Okay, so we're going to start from time step t-1 and simply ask the question, what is the best policy? Now, the best policy at t-1 is obvious. Take the left action and go to the trophy. So that's easy. Now we go back one time step and ask, what is the best policy that we can do from t-2, given that we already have t-1? And that too is going to turn out to be the left action, since taking the left action takes us to the trophy. And then we can keep going backwards, ask the same question at t-3, given t-2 and t-1, what is the best action? And that's to take the left, and so on and so forth. So in only a polynomial number of time, by restarting from the expert distribution, we are able to recover the optimal policy, which is pretty cool. So this is what we refer to as a lazy planning step, right? We're never visiting all the nodes. We're only restarting from the expert states. Okay, so PSDP is lazy. Instead of searching all the states to find the best policy, we're just doing better on states the expert visits. Can PSDP help us make model learning efficient? Because, so if you recall, when we wrote down the theory was asking us to solve for the optimal policy at every time step, right? So it's not clear to us that being lazy is a good idea for model-based learning. But I'll show you first intuitively and then mathematically that indeed the answer is yes, it's actually being lazy works perfectly fine for model-based learning. Okay, so let's go back to our previous example where we have a model that has learned all of these shortcuts to go to the goal, all of these mistaken shortcuts, right? Okay, now we're, instead of computing the optimal plan, we're going to do lazy planning. So we're going to begin with these expert states and run our lazy planner. Our lazy planner is going to come up with this sort of a policy. So it takes the shortcut at the second time step and goes to the goal. We run this policy in the real world, eliminate this shortcut, and get a new model. Again, run lazy search, polynomial time, execute the policy, eliminate the shortcut, run lazy search, polynomial time. And in just 2 iterations for this example, we have converged and found a model that gives us the optimal policy that always takes the left set of actions, right? So what's interesting here is that this is the final model that we learn when we plan with a lazy planner. Notice that this model is does not match the true dynamics of the world. I mean, there are still lots and lots of shortcuts, as you can see, but in some sense, the shortcuts are irrelevant because the policy that we have learned will never visit those shortcuts, right? The policy will only stay on the leftmost branch, right? And so in some sense, this is the trade-off that we are trying to exploit, that we don't actually need to visit all the various states in the model and eliminate all sorts of inconsistencies. We just need to make sure we eliminate the portals that are on the on the states that the policy is likely to visit. And that's sort of the key insight that allows us to be lazy. Okay. All right, so intuitively, this seems promising, but can we rigorously, theoretically prove that being lazy is a good idea for model learning? And in trying to do this, we spent a lot of time. In fact, spent almost a year trying to look at the math and came out of it at the end with a fundamentally new lemma in model-based reinforcement learning that we are very excited about. So let me kind of show you the lemma and contrast the differences from the lemma we saw before. So I'm going to call this lemma performance difference via advantage in model. Okay. And so this lemma is, again, we're going to look at these two terms of the performance of the expert in the real world minus the learner in the real world. And again, bound this as a sum of 3 terms. But the first term is no longer the planning error, but in fact, it's the advantage of the expert in the model. So the first term is saying on states that your expert visits, how much better is your policy pi than the experts on those states? Okay, which is precisely the term that the lazy planner aims to optimize or gives a guarantee on. Okay, so that's the first term. The second and third term remain the same. So the second term says how good is your model on the states your expert visits, and the third term is how good is your model on states that the learner visits, and they remain the same. So this is really interesting, right? The math, in some sense, by doing an alternate expansion of the performance difference lemma, we are able to prove that being lazy suffices to bound the performance difference. In some sense, it gives us a tighter bound on the performance between the expert and the learner. So that suggests this, new algorithm that we call lazy model-based policy search, or LAMPS. And the idea of this algorithm is replace the planner by a lazy planner and keep everything else the same. So you're going to collect data from the expert, you're going to collect data from your learner, you're going to fit a model on both of this data, and then do lazy planning with this model to update your data. And that's all. Okay, so since we're running short on time, I'll just go right to the results. So one of the first key results is that our method LAMPS finds much better policy with fewer samples and fewer computation. So we looked at the same problem as we did before of the helicopter doing the funnel movements. We used, we did the same policy as before. So unlike before, where planning with this model required calling ILQR that had several forward and backward passes, lazy planning in this case is simply calling LQR. So that's just the one backward pass. That's a key difference, right? And we showed that that if you run LAMPS, you're able to, with the same number of real-world interactions, you're able to compute a policy that has a lower cost than working with SysID with fewer number of iterations, and it's almost close to the expert in this case. And you get very big computation wins because you're doing LQR versus ILQR. So with number of real-world interactions, the number of LQR solver calls for LAMPS is much lower than the previous method. And there's one more interesting result, which is that the LAMPS is not actually guaranteed to find the optimal policy in your model, right? So ILQR finds a much better policy in the model, but the key insight is that better policy is not necessarily as good in the real world, because ILQR is sitting and wasting time exploiting shortcuts in the model that don't really exist in the real world, whereas LAMPS just becomes lazy. It just tries to do better on states the expert visits. So that sort of shows up in the experiment, which is pretty cool. Oops, sorry. So we ran it on a suite of Mijoko tasks, and in general we see lamps converge to have better performance with lower number of time steps. We see big performance gains on examples where exploration is required. That's where we see sort of lamps being able to really pull away from state-of-the-art model-based policy search. That shows that the performance gains are for problems where exploration is a big challenge. And okay, so that's sort of just to recap. We talked about model-based learning with planner in the loop. We showed that one of the core problems in model-based learning is this exponential complexity of planning. We then had a simple idea. Can we be lazy, replace this exponential complexity, replace this XT planning step with a polity lazy search step, and propose a new method lamps that on theory is sound, and on a number of evaluations seems to clearly outdo model-based learning with planner in the loop. Okay, in the last few minutes, I wanted to quickly touch on another fundamental challenge, and in some sense, this is the challenge we wanted to. This was actually the core challenge we wanted to tackle, which is this issue in model-based learning of mismatched objectives. So in all of the work that we just saw today, whenever we are fitting a model, we typically use log loss, or which would be equivalent to using an L2 loss in continuous settings, or classification loss in discrete settings. But ultimately, we don't really care about log loss. We don't really care about matching exactly the state transitions in the real world. In fact, what we care about is matching the performance of the expert, right? Matching values rather than matching one step, matching the actual transitions. Okay, so how can we? Does our approach, or does a new theorem help us change the objective in some sense for model-based learning? So just to motivate this question a little bit, let's say I show you another MDP, okay, and this is a much more simpler. It's also a tree MDP, but in this MDP, you have taking the right action at the root node results in death, and taking every other action is fine. It's no cost at all. Okay, so let's say you're in this MDP. Okay, now let's say there are two model candidates that you're deciding among, right? One of the candidate is model A. Okay, model A is a model that exactly gets the transition right on every single state except the root state, right? So it incorrectly predicts that going right results in no death, while going left results in death. So it switches the order, but it matches the real world on every other state. So the other candidate model is model B. Model B is a problematic model. So model B gets transitions wrong in every other state except at the root state, right? So at the root state, it correctly predicts going right results in death, and going left is fine. Okay, so let's say you have these two models. If you were to look at these two models and say which of these models has lower log loss, right? So lower L2 loss or classification loss, clearly say model A has lower log loss, right? It almost exactly matches the real world, except it makes one critical mistake at the root. So if you were to plan with model A, you would actually take the wrong action, and you would get a really, really bad policy. Now take a look at model B. Model B has very high log loss. It's not agreeing with the real world on almost every state. But in some sense, that doesn't matter, because it gets the transitions that matter correct which is the transitions at the root. So if you were to plan with model B, you would actually be performing almost optimally. So we would much rather prefer that our model learning algorithm picks model B. But today, if you're using L2 loss, that will not be the case. And pretty much almost every method, almost every state-of-the-art model-based learning method out there would pick model A, unfortunately, right? So can we change the loss function for how we fit the model, but do so in a principled manner? And the interesting thing is the lemma that we came up with actually solves this problem as well. So that's really exciting. So it says that, so we are looking at the same lemma before, where we're looking at the performance of the expert minus performance of the learner. And now I want you to focus on the second and third term. Instead of looking at the total variation distance, the second and third term says what you should be doing is you should be matching the values, the value differences, instead of the L2 loss or something like that, right? And so we can use this lemma to come up with this with a really simple change to our LAMPS algorithm, where we change the loss function that we use in the model from an L2 loss to a value loss, where the value comes from the value function of the current policy pi, right? And this using no regret analysis, you can sort of show that this will give you a guarantee on the true performance difference. And so we call this method LAMPS LAMPS with moment matching. And so the combination of two things, lazy planning and value loss, gives you this sort of gold standard algorithm that not only is computationally efficient, but also optimizes for the true value, optimizes for the right metric. Okay, so just to recap, we talked about two challenges. Planning is computationally expensive, and mismatch objectives in model-based RL. And these have been fundamental challenges in model-based RL for a long time. And our core contribution is a new lemma called performance difference by advantage in model that seems to be a really promising lemma, because it gives us solutions to both of these challenges. It tells us to be lazy to solve challenge 1 and to match the value loss to solve challenge 2. And so I would highly encourage you to check out our CML paper that kind of talks to the theory and talks through the detailed implementations. And I'll end on the note so we talked a lot about model-based RL, but the ideas that we talked about go beyond model-based RL. So we also have a paper at ICML on imitation learning that in some sense uses a very similar technique of lazy search to reduce the exponential complexity of inverse reinforcement learning to polynomial complexity as well. And so the idea between these two approaches is building on the same core insight, which is both model-based RL and inverse reinforcement learning requires calling this complex, computationally expensive planning in the loop. But we don't need to solve that. We can actually leverage expert states by restarting from them to efficiently solve both problems. And there are lots of interesting questions that we can ask. We're just at the beginning stages of this work. There are practical questions we can ask on, what can we do when we don't have optimal expert distributions? Would the theory work? What can we do when restarting is difficult, especially if you're dealing with real-world robots? These are some of the questions that we are thinking about and working on. But with that, I would like to come to an end and thank you for your time, and I'd love to take any questions. Thanks.
Thank you, Sanjiban, for the great talk. Let's open the stage for questions. You can either raise your hand and ask, or just post the question. I will read it for you. So who wants to be the icebreaker? So maybe I'll do the...
I would start.
Emilio, go ahead. Yeah.
Okay, Sanjiban. Well, first of all, thank you very much for the talk. Very stimulating. Now, so when you make the claim that you are like converting, some problem that has exponential complexity, right, to do something polynomial, I mean, it looks like you're claiming that NP is equal to, P, things like that, right? So, which I think you're not. So what do we lose, right? Or, how,
Yes.
where is the trick, or where does this fail, right? Or
Yes.
I was wondering, because, essentially you're relying on these expert states, right? So
Yes.
maybe you're hiding some of the complexity into choosing those expert states in a sense, right? So
Yeah.
where is the trick, right?
Yo, that's a great question. So I'll answer it in two stages. So the first thing I would say is when we were first trying to do this trick of using the restart distribution, we thought in theory we will end up with a performance bound, like in some sense an additional term in the performance difference bound. And we had that initially, which was difference between planning error and this lazy planning performance. And we thought that would be an additive bound that will show up, which could be very large, right? However, I think the one of the interesting thing is by doing an alternate expansion of the performance difference lemma, you can get around this bound because so one of the contributions of the paper was to show a different way to expand performance difference than has been done before, and to show that you can actually write it in terms of this this advantage term that's measured on the distribution of states the expert visits, right? So this alternate expansion actually allows us to very confidently use lazy search without incurring an extra performance gap. In fact, it's an exact equality that we proved. However, your question is really important practically, because practically restarting from the expert states. So what do we need to actually implement this algorithm? We need a distribution of states where we need distribution of states coming from an optimal policy pi star. And that can be very restrictive. In some sense, what's happening is we are asking the expert to solve the exploration problem for us, right? And that can be very restrictive. So I think that's where that's where the trick is in some sense, right? If we did not have, let's say we did not have any such states from the expert, we have no choice but to do exploration. I don't think we can get around exploration at all. And so again, we would fall back to the exponential t. So the question is, what can we do in the middle ground where we don't have data from an optimal expert, but maybe we have coverage, like we have data that covers the expert. Can we prove something that looks like a best of both worlds guarantee, right? That looks like, we can do as good as learning the traditional model-based RL with planning in the loop, and we run both. We run the traditional algorithm and we run this lazy search, and we have a way to combine the results that gives us the best of both worlds. And that's something we are working on. I don't think we have the answer, but that would be a direction to look at. So yeah, so I think, and in practice, restarting, if we were working, today we're working with a model. If we're working with a real robot, restarting from arbitrary states is challenging. Like imagine you're trying to train your robot to do a backflip. You can't restart your robot from mid backflip. That's just not possible. So if you don't have these restart access, what can you what can you do in that case? And I think that's also an open question. It's not clear you can use this method then.
Okay. Thank you, Sanjiban.
Yeah, it's a great question. Thank you.
Any other question? My question, okay, I have a question which connects a bit to what Emilio asked, and it's in the practical applicability. You answered a bit already, but I was wondering whether you figured out already what is the perfect application, or where you really save a lot. right?
No,
What are
that's
you
a great
thinking about?
question. I think I didn't really talk about what are the applications we are looking at, but I think one of the big applications we're looking at are where you have a robot that's sort of working in a very rich, high-dimensional observation space, in the space of images, and predicting predicting transition models that predict higher image will evolve. It just hasn't worked in practice. It's a very difficult problem. Ideally, you would love to learn models that learn some sort of a latent dynamics model that is instead of trying to use reconstruction like losses that we typically use, because that's sort of not the point. The point is to match the value loss, right? And so what we're trying to look at is, can this algorithm give us a model that's effectively able to learn this latent dynamics model, such that if you plan with it, you're able to match expert performance. And so these complex observation spaces really been our focus. It's obviously very relevant to robotics, where you're learning visuomotor skills, for example, manipulating things like deformable objects and so on. So that's sort of one application. I'm looking at it in my lab, but I think more broadly, models are of interest to many others in the community. So we're hoping this can be useful to just beyond just that application. Yeah.
Thank you. That's exciting. Any other maybe final question for Sanjiban? Doesn't look so. I think you left your email in case people want to reach out for.
Yeah, absolutely.
Maybe
at my email, I'm
tonight
happy to...
they come up with a question. And it's
No, I'm happy to take more questions, and I want to thank you for hosting me, and thank you for everybody who came. This is super interesting. If you are at ICML, please do come stop by, and we'd love to have more discussions on this. But yeah, thank you again.
Thank you very much, Sanjiban, for the talk, and thank you everyone for participating. See you all next week.
See you. Bye-bye.
Bye-bye.